Okay, so I think we can get started first, and then we have already so roughly 20 people, and then the other people will come also during the talk. So maybe I can first give an introduction to the speaker today, and then the speaker can take over. So Lauren is is a fifth-year PhD student at the University of Washington in computer science and also engineering. So working with Professor Ye-Jin Cho and also Ali Fahadi. He's interested in enabling machines to learn language grounded in a common sense understanding of the world. His recent line of work includes benchmarking analysis and also model building, and spans across natural language processing, computer vision, and also artificial intelligence. His work has been funded by NSF Graduate Fellowship and also appeared in several media outlets, including Wired, The Washington Post, and the New York Times. His recent work, MERLOT, also attracted a lot of attention by pre-training a large-scale model on large-scale video text parse. And then without further delay, I'm going to hand over to Lauren. Yeah, please go ahead.
Thank you so much, Jeff, for the kind introduction and for inviting me here. This is super exciting. So today I'm going to be presenting on learning common sense understanding through language and vision. Going to cover some of these recent papers and hopefully have some time for a good amount of time for discussion. And if not today, then I'll be around tomorrow as well, or you can shoot me an email or something. All right, so great, let's get started. Okay. So I couldn't figure out a better way to start this talk than the standard, machine learning has made a lot of progress and it still falls short intro. So let's roll with it. You know the drill. There's been an exponential increase in model scale over the last couple of years. And as a result, we now have kind of a strong performance on a variety of previously pretty challenging tasks, like multiple choice QA in text, possibly outperforming humans here. Or in vision, these recent new exciting modeling approaches have let us get kind of Webley supervised classification and detection that is pretty good. Definitely a lot better than it was a couple of years ago, where you needed lots of supervised data in order to get these models off the ground here. And in the vision and language space, there's been a lot of really exciting work, particularly from people at Microsoft, exploring what models can do when they're provided images and language as inputs. So typically this is often an image captioning domain. So kind of like learning to generate captions from images or learning to fill in the blanks, and then turning this into performance or strong performance on other tasks like VQA. Okay, and so here's the whole "it falls short of humans" comes in as part of the intro, right? Because while these capabilities are really exciting, we as humans are kind of doing something completely different. We're learning not primarily from web text or even web data at all, but rather by interacting with the world, using our senses to take in rich experience that updates our beliefs. And this often, gets stored in text, and we often learn in text, but it's not the only way we learn. And from this experience in our lives, we're able to learn multimodal representations that are also common sense. So they cover not just images or multiple choice QA tasks or captions, but also events and situations that take place in our daily lives. And so kind of in this talk, I'm going to be discussing a couple of different ways to help bridge these gaps to move us a tiny, tiny bit closer towards these rich capabilities that humans can do. Okay, so this is kind of the rough outline, and it corresponds to two papers that we have available right now. And the first one is called PIGLeT, Language Grounding Through Neurosymbolic Interaction in a 3D World. And we presented this earlier this summer at ACL 2021. Okay, so here's this diagram I showed earlier. And you might say, one of these things is not like the other. And I would kind of characterize here the outlier as being written language. And we can kind of more or less think about it as discrete symbols, whereas everything else is kind of grounded meaning, continuous. It's a bit subjective, and it breaks down into a bunch of subcomponents, these senses that are also continuous. This gap was summarized by Steven Harnad in 1992 as the symbol grounding problem. He's asking, how do we as learners, either humans or machines, connect the world of written language, which is composed exclusively of these discrete symbols, to the world which is messy and continuous? Now, there's been a lot of recent attention paid towards this dilemma, particularly with Bender and Kohler's ACL Best paper from last year. They described this really engaging thought experiment about an octopus, and it learns about the land world exclusively through symbols passed on an undersea cable. And so while it can read a lot of these symbols and it's a really smart octopus, it can never truly understand the meaning that these symbols refer to, what it means to do stuff in the land world. And today's language models, they argue, and I would kind of agree, are to some degree like this octopus. And changing this picture, moving us towards a non-octopus-like model, I would say is a key technical challenge, but one that I'm pretty excited about. So in this work, we study a different category of learner. So what we do is we propose to learn the meaning of language through interacting in and interacting with the world. So what I'm showing you here is a video of someone, a robot, I guess, filling up a mug in a 3D world. We can keep track of the state of the mug, either in symbols, like the mug is picked up, or in images, or both. And we want to connect this learned experience about what mugs are and what mugs do to language, such that when we read the word mug or say it, we have a grounded sense about what that means, what that word mug is actually referring to, and maybe more ambitiously, what that whole sentence might be referring to. So we propose to learn this capability in THOR. THOR is an interactive 3D environment developed at AI2 with 20 actions and 125 object types. So in THOR, actions are to some degree contextual, which means kind of like English verbs or verbs, I guess, in any language, what an action does depends on the object that it refers to and their state. And objects have a state that is expressed by 42 attributes that are binary or multi-class, like, is it broken? Yes or no? Cool. So in this part of the talk, I'm going to discuss how to model and then how to measure using this transfer for a few interesting things that involve learning from the world and transferring that to language, and to some degree going the other way. We'll go into these things in a little bit more detail soon, but I want to first talk about the PIGLeT model. So again, our model is named PIGLeT, and the key idea is that we're going to learn two interconnected components from different data sources. We want to first learn a module for intuitive physics, and then a separate model for how language works. And these two models will allow us to kind of perform this transfer, and we can tie them together with just a tiny amount of paired data involving both situations grounded with language. So let's dig right into the physical dynamics model, which you can think of as a model that tries to predict what might happen in the world if you take a specific action. So in this example I'm showing you, I have an egg, it's at room temperature, it's not cooked, it is broken, and it's on a pan. What happens if you heat up that pan, though? Expressed symbolically in the, I guess, API of the game as heat up, comma, pan. Now, the next state that's generated by the API is that the egg has a temperature of hot. It is now cooked. Is cooked equals true. And so what we want our model to do is to be able to generate this post-condition state given the preconditioned state and the action. So how are we going to do this? So here's the model in question. You can kind of think about what our approach is similar to an autoencoder. We're going to encode the objects in the scene with a transformer, and we'll encode the action with a multi-layer perceptron. We'll extract hidden states from both, and we'll pass the result into a multi-layer perceptron that will predict the new object state for all the objects. And then we can then decode that new object state into a symbolic representation with another transformer. We can then pre-train this model over 280,000 interactions, basically all the objects in the scene, and then predicting each label, each attribute for each of these objects. And it's all using a cross entropy loss, or I guess a series of cross entropy losses, one per attribute. Cool. But how do we combine this with language, which is the focus of this part of the talk? Well, what we want to do is we want to use the same hidden representation. We want to make it so that our model turns this sentence, the robot heats up the pan, into kind of a function representation, similarly to how it embedded heat up comma pan into to kind of another function, but is represented at the end of the day as a vector. So we'll adapt a pre-trained language model that turns this sentence into a vector representation of that symbolic action. We can then just feed it straight into the action applying multi-layer perceptron. And then we can use that model to decode the vector representations of each of the new objects in the scene. So given the update, given their updated states, to generate the new sentence, the pan becomes hot and the egg gets cooked. Cool. So that's kind of the idea about how we're not just, so we have a physical dynamics model, we have a language model, and we want to tie them together to be able to do this transfer. To tie them together, now we're going to fine tune it on just a small amount of paired data, which is language with situations. We have both submodels that we've pre-trained separately. We'll fine tune them all together on this set of 500, and the total model is BERT-based sized. Cool. So that was a brief sketch of the model. There's more details in the paper, of course, but I want to quickly show you that how we can use this model to predict explicitly exactly what happens next to an object given an event. Okay, so let's go over a concrete example about what our data and what this problem looks like to get us all on the same page. So here I'm showing you a sink. It's filled with liquid. And we have a mug, and it's also filled with liquid, and it's picked up. The goal is, I'm going to give you give the model a sentence. The robot empties the mug, and it has to predict what's going to happen next to all of the objects. And so what it should say is that the sink will not change, but the mug will. It shouldn't be filled with liquid anymore. So we can easily evaluate this, whether the model is correct, evaluate the scores of a model by just checking whether the model gets all attributes in an object right. So let's look at how well various models do. So here's a quick summary of the results. Some more baselines are in the table, in the paper. So first, if we say that objects never change, we'll be right 26% of the time. So sometimes objects don't change. We then adapted GPT-3 to this task, and it actually does worse than random. So we can't fit in that many examples within the prompting window because it's only 2,000 tokens or so, and there are actually a lot of attributes here, even in our kind of text-to-text representation of it. But with the examples that we can prompt it, it can't seem to learn the world dynamics. Now, if we could fine-tune it, it does a lot better, and we can kind of guess about how well it might do by looking at T5. So this is a model with 11. Yeah. Yeah, go ahead.
So for GPT-3, did you just call the GPT-3 API, or you can fine tune it or somehow do the inference?
Oh, we weren't able to fine tune it. We had to use the API, which I think maybe it can do fine tuning now, but yeah, we only were able to do the prompting thing. I can only guess about how it would do based on how well T5 does if you fine tuned it.
Okay, thank you.
Thanks.
Yeah. But T5 was fine-tuned, right?
Yes, T5 was fine-tuned. 11 billion parameters. So in other words, yeah, so T5, if you can fine-tune it, it does quite a lot better, 64%. And it's fine-tuned on the same paired language and situation data that PIGLeT gets. So it has enough data to be able to learn the text-to-text format of the task, how to spit out probably a valid, I guess, representation of the objects. But it still makes a lot of mistakes at transferring its text-based knowledge to the grounded world. Our model gets better, or is better by about like 81% accuracy. So it's a pretty neat result. Our model, which is base-sized, learning through physical interaction, it outperforms a model that's 100 times bigger by over 10%. So what does this mean concretely so we can get all on the same page? So let's go over that same example from earlier. PIGLeT is able to get all of the objects right. It correctly says that the sink will not change and the mug will change. The mug is now not filled with liquid after the robot empties it. But T5 learned something interesting when it's trying to transfer its text-based knowledge with the same amount of fine-tuning data to this setting. What it does is it says that the sink is now not filled with liquid. So kind of through text and through the same fine-tuning data, it learns that emptying liquid from an object makes all objects in the room empty. And maybe that's true for some of the things that it saw during fine-tuning, but it's not quite true from kind of the rules of how the environment works. And so PIGLeT is able to learn this, and T5 with 11 billion parameters isn't, even after fine-tuning. Cool. So there's like a couple more things that the model can do, and I want to go over one more capacity in this talk. So PIGLeT can write an English sentence summarizing that state change.
Hi, everyone. May I ask you a question?
Go ahead.
Oh, is the PIGLeT really learn the 3D geometry, or it just learn the relationship in terms of the text?
That's a good question. Yeah, so what we did for this work is we're just using the symbolic representation of, so not like, not images quite yet, but rather just this kind of attribute level view. And the reason I would say is because, well, I guess we wanted to kind of decompose the kind of errors that the model makes into cleanly like one bucket or the other. And it made sense just to treat it as all models are going to get the ground truth view about what's going on in the world. But I think it would be really exciting to try like something 3D, like, or even just like a 2D image provided to the model.
But this essentially, you basically still turns the image into a bunch of text, properties, as what you said, and after that, it's just basically pure NLP, text processing, and figure out the relationship, right?
True. I mean, we did kind of, like, for our model, we kind of did break it into, I guess, 42 distinct attributes, so kind of different, I guess, dimensions, if you will, whereas for a T5 or GPT-3 type model, we did turn it into a text-to-text representation. But yeah, if NLP is anything that is, what is it, that you could write down, then I guess it would be NLP. Sure.
Okay, thank you.
Yeah. Cool. So it gives, great. So the last capacity in this component of the talk, PIGLeT can write an English sentence that corresponds to the result of an action. So here's the same example from before, but the other way around. Given the symbolic action, empty mug, we want our model to describe the result in English, going fully from symbols to natural language. So here, the sentence that we wanted to write might be something like this. This mug is no longer filled with water. So compared with T5, our model does better on human evaluations, both in terms of fluency and faithfulness. So it's kind of cool, right? It sounds better and it's more accurate. Here's an example. So from the same thing I was talking about earlier, PIGLeT generates a sentence, the mug is now empty. So it's great. And now T5 makes the same mistake, but is now writing it in natural language. It generates a sentence, the sink is now empty. Again, likely because while it's good at generating sentences about things being empty, it can't seem to do that fundamental task of linking that sentence with the grounded action of emptying the object in simulation. And so that's kind of all this is. This paper is about performing this grounding or this linking, if you will. So brief summary of what I've kind of talked about in this portion of the talk. We have an approach that learns about the world via interaction versus the kind of dominant approach of learning about the world indirectly via what is being written in language. And PIGLeT learns a lightweight factorized world model, two different components, or a different component for predicting what might happen next versus a single heavyweight and entangled model. And this lightweight world model allows us to do other cute things like generalizing to new concepts, which is something we talked about in the paper, but I don't have time for in this talk right now. Like I say, this is a DAX, this water bottle here, but I don't tell it it's a water bottle. And then it can do pretty well at predicting or what might happen to a DAX given its experience interacting with, say, water models. Yeah? Okay. But on the other hand, these other models kind of have limited generalization to new concepts. If you define what a DAX is, for instance, in text, GPT-3 can do pretty well about generating sentences from it, but you can't, for instance, show it an image of a water bottle and say it's a DAX and then ask it to generate something coherent, because there's no way for it to take in that as input. Cool. So learning physical common sense through interactions, higher performance with much smaller models. So we can talk more about this later, but I want to first briefly transition to the second part of the talk, and we're going to be discussing how we can learn vision and language grounded in events and daily life rather than just static scenes, and all without any human labeling or supervision. So this is from a new paper that we posted to arXiv this summer called MERLOT, Multimodal Neural Script Knowledge Models, by a bunch of people with equal contribution between myself, Ximing Liu, and Jack Hessel. So what do I mean by knowledge about events and activities? Kind of old by today's standards, but the key example that I think about still is this example I'm going to show you from visual common sense reasoning, data set I worked on and helped create a couple of years ago. So here's a snapshot in time of a dynamic scene. And even though we don't have the full context about what's going on, we can use what we do know about it to answer the question, why is this person pointing? Okay, it's hint because he's pointing because, what is it? He wants to tell the server whose orders whose, but we could kind of infer some variant of that, or maybe some other clever reason from the scene. Okay. Answering this question is hard because it requires a lot of layered inferences, not only about what is literally happening in the scene, but also about what might happen in the scene, about how the world works. Sure, we can detect the objects. There's a syrup bottle, the ketchup, some mustard, etc. We can classify what setting we're in, I guess a diner, right? And we can point out a few relationships, like here's someone holding food and here's someone holding syrup. But these don't tell us the full picture about how to solve this or answer this question. I want to argue today that one of the missing pieces for answering this is multimodal script knowledge, which is common sense knowledge about events, including what do people do at restaurants and why? What might be going on in this event and what might be happening next? What are people's roles? Who is doing what to whom, etc. The name that we chose references vanilla script knowledge intentionally. And this is something that was written about decades ago, to some degree still today. And back in the early days, people kind of formalized it with papers like this one. So this is famously by Schenck and Abelson in 1977 called Scripts, Plans, and Knowledge. And they describe something, interestingly enough, that it's kind of like what you would need in order to unpack this VCR example. There's a restaurant, people have these different roles, and you at first have to enter the restaurant, and there's like a lot of different components of that. But the format of this was kind of weird. It's only expressed in this kind of hybrid of English and assembly language, I guess. And likely, if you've been to a restaurant, especially recently in COVID times, you know that things don't always work this way. They're not necessarily this structured, and there's often a lot of new rules that we have to reason about. So I would say that there's two key changes that we kind of have to make from this formulation. We need script knowledge that's multimodal, that covers aspects of life through a variety of different viewpoints and senses and over time. And it needs to be neural, allowing us to learn more complicated rules, but also exceptions to them when there might need to be exceptions. And so in this project, MERLOT, we propose to learn visual reasoning up to and including this kind of multimodal neural script knowledge, and all from YouTube. So from 6 million YouTube videos, we're going to learn a bunch of things. We're going to learn first the basics of recognition level knowledge. So for instance, we have in this video, I see a person, a pan, a burner, a stopwatch, water pitcher, thermometer, etc. But our next goal that we say is equally important is to learn multimodal script knowledge about how these objects combine together in the context of the frames and what's said. So there's a person, and that person is probably in his kitchen, and I use measuring how fast the water is boiling. So we call our model multimodal event representation learning over time, or MERLOT for short. And the result that I'm going to be talking about very, very soon is a model that has strong out-of-the-box capabilities for temporal common sense. And when it's fine-tuned, it gets strong results on 13 tasks. So it's kind of exciting. So first, I'm going to discuss a little bit about our pre-training strategy, where we ideally learn everything from recognition to cognition without needing any label data whatsoever. So here's kind of a brief outline of the setup and how we're going to use YouTube in the first place. Given a video on YouTube with a transcript, we're going to split that video into different segments. Got the segments right here. And each segment corresponds to around 32 BPE tokens. And we're going to extract the middle image frame from each one. So maybe the first one is I'm going to compare electric and induction stoves. I'll use a stopwatch to time how fast my electric stove boils water. In goes the cold water. And it took 4.5 minutes to reach full boil. So that's kind of the thing we're working with here. And so again, we're extracting the middle frame from each of these segments. And I want to say first briefly that this strategy is a bit similar to some concurrent work that people here worked on, Clipboard, which also works on single frames rather than the entire video. But the key difference in this work is that we took an approach where we're trying to do this learning strategy without static images or without training on any manually labeled data. So first, how are we going to learn this kind of baseline of knowledge or visual knowledge at the recognition level? So we'll adopt an approach similar to CLIP. We want to encode each image frame separately, and we want to maximize similarity with respect to an encoder of the text. This is found a lot of work, not just CLIP, for instance, has found this kind of approach works pretty well on a variety of different like vision and language, or even I guess any task where you want to have an image encoder. But there's a problem here owing to the contextuality of videos. So the problem here is that the ASR caption at the same time step, in goes the cold water, doesn't really say all that much. Says their water, sure. But a lot of the things we really want to know about in this image came from the previous caption, the stopwatch, the fact that this person is using it to time something, and the fact that they're on an electric stove and boiling water. So what we ideally want to do is kind of use both. We want to handle everything. So in this approach, what we do is we handle everything on the text side contextually. So we're going to treat the text as one long sequence with individual class tokens or CLS tokens, I guess, for each segment, and we can pull from them. So here are the CLS tokens, for instance, they just come at the end and they kind of split the different segments up. I'm not going to show them all now, but you can imagine that they're there in future slides. Cool. So we can now take this objective and apply it at the same level to learn contextualized language, or sorry, to learn the similarity between contextualized language and individual image frames. And we'll later show that we can intermix this objective with other objectives for kind of higher order visual reasoning to learn recognition level stuff at the same time as higher level script knowledge. Cool. So that got us supervision for the backbone image encoder. What we want to do next is learn a joint representation of common sense, vision, and language. So just like as we as humans watch a video, listen to the transcript, and we can kind of picture what's going on physically, say in this person's kitchen, what they're doing and why, we want models to be able to do the same thing. And we use two different objectives to guide this level of learning. The first one is pretty standard, mask language modeling. So I'm going to take out some words like minutes and boil. And the model must be able to then predict those words. Ideally, it's going to predict it using knowledge that it gains from the image. And it's been used in a lot of past work, both language-only models like BERT, as well as past vision and language papers like Uniter, Oscar, et cetera, a lot from here. However, there is an issue that we run into in the in the video domain, and there's more details in the paper, but I'm going to touch on it really briefly in this talk. You have to be very careful with how you select the words for masking. And the reason is because spoken text is often highly redundant. So it might look like this. It might look like it took 4.5 minutes to reach full boil. Okay, boiling that water took 4 minutes. Now we'll blah, 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 right? So the redundancy means that models can often cheat by just using redundancy that's in text, and they often don't actually need to refer back to the image, the video frames. And that's kind of an issue. Why this is? Well, there's actually, I think I have a bunch of, there's a bunch of reasons I can think of. I think it has to do with kind of the temporal and kind of lossy nature of speech. We can only go forward in time, we can't go back. So speech is kind of necessarily a little bit less condensed than is written text. So Grice's maxims and all that, but I don't have time to go into that too much for this talk. Basically, we have a trick. Yeah.
Yeah, so I think so Hamid has a question.
Yeah, sorry, go ahead.
Yeah, Rowan, I just missed, what was the image encoder?
Oh, it's just a CNN plus visual transformer.
Okay, thanks.
I should have mentioned, yeah, sorry, trained end to end with everything.
Yeah, thanks.
Yep.
So did you try a pure vision transformer?
I did, and it actually didn't work quite as well. I'm not entirely sure why, and I think it might be, well, actually, we can kind of discuss more offline. I have a bunch of reasons, but I wasn't quite able to pinpoint down the reasons. The other thing that we wanted to do deliberately with this work, so kind of why I didn't explore it too much, is we wanted to make our backbone more or less the same as other backbones that other people have used in the past. So, you know, you often have this like a big object detector model, followed by some like kind of fully connected layers that operate over region features. And this backbone is actually really expensive, which was kind of discussed about in a couple of different works about kind of grid features. And so I think like to make it kind of like have more or less like the same, to kind of be in like the same ballpark, that's why we added the ResNet sub backbone, such that, hey, we're using a ResNet backbone too. Now, I don't know whether that was like the best approach, but we kind of tried to do an apples to apples comparison as best as we could. We couldn't quite do the same detector backbone, both because we didn't want to use any object detection supervision and because it's really expensive to run it like at the resolution that it is ran on. So basically this kind of approach, you get like, it runs like, I think 10% of the flops or something. Yeah, it's kind of wild. Sweet. And I can talk more about this later. But yeah, our solution here, so this problem of kind of redundancy that exists in the speech domain was very frustrating to us while we were working on this. Because it means, yeah, a model often does, like, in the worst case scenario, the model doesn't need to look at the frames at all. And so our solution was to try a slightly different masking approach where we try and mask all of those redundant words. So we'll use a measure of importance computed by the attention weights in the previous step that were for the first objective, basically saying, okay, words like boiling and minutes are really concrete, so let's try and mask all of those. And this helps guide the masking process. And so we have, again, more details in the paper. All you need to take away from this is that you have to be very careful when you're masking in the speech domain. And I don't think I have a really good solution for this besides this like little hack we used quite yet. Okay, so that was for the masking. And now for the third and final objective, we're considering learning kind of temporal knowledge about like the order for what events make sense. So what we'll do is we'll optionally provide the models with the frames in sorted order or shuffle order. And the model is going to have to learn to order these frames. So in this case, I flip the frames, frame 2 comes first. Now, a tiny bit of detail here for how we did this, how we're providing this information. We did this through position embeddings. So we can easily tell the model that things are not shuffled by giving the model the correct position embeddings, like t equals 1, t equals 2. And, you know, just like same with like normal BERT style or whatever, the position embeddings are just added with the other embeddings. If we want to, however, tell the model that things are shuffled, we'll have to give them a dummy position embedding here, like t equals I don't know 1, or t equals I don't know 2. And then the model will guess that frame I don't know 2 comes first. So telling the model there's no specific ordering information that you can know between I don't know 1 and I don't know 2, but those are different frames. So it can learn to kind of split up those representations. Cool. So those 3 objectives plus the image encoder and a joint vision and language encoder, that's MERLOT. We're going to use a 12-layer base transformer for all of this. So 12 layers for the joint vision and language encoder, which actually shares parameters with the text-only encoder, and then a separate image encoder that is the vision transformer plus the ResNet. And we'll train everything end-to-end on 6 million videos. Cool. So that was the pre-training strategy. And now I'll kind of briefly touch on the evaluation. So here's the first thing we tried. It's kind of a fun little party trick. It's where you try and zero-shot unscramble some visual stories. So we kind of use this task formulation. Given the text of a visual story, match images to text to tell a narrative. So this is the right story. This old man was riding an escalator. He was almost at the top. His kids were already at the top. At the top was a train station. They then got in the train. And I've got 5 jumbled images that correspond to these captions, and the model has to put them in the right order. The right order is this one. So we have someone riding, like kind of an image of an escalator. It's in the background. He's riding to the top. There's the people at the top. I guess they're his kids. There's the train station, and then they got on the train. And this is just from this task that the crowd worker said this was the right order. So our model is able to actually get this right without fine-tuning using the unscrambling objective that I just talked about. In order to make this work, it has to actually do some amount of visual co-reference over time. So it has to kind of look at both of these captions, the old man and he. It has to link them both to this guy right here, which is kind of interesting. We compare this with a bunch of other baselines, notably CLIP. And so what our CLIP baseline does is it tries to match all of the frames and captions independently. And it does pretty well at this, but it has to solve a much more difficult task than we do. Because it matches everything independently, it has no inherent idea that he in the second caption refers to the old man in the first one. So it can't like do this kind of vision and a language co-reference over time, and it also kind of can't take advantage of like priors that you might have over the vision side, and so it gets this one wrong. Still very impressive, but it is. But what we want to say here is that we're able to solve by taking advantage of knowledge about events and what is likely to happen over time. We can do quite a lot better at understanding this. And so here's some numbers. If we compare the distance away from sorted order, our model does the best, I guess, at 0.5 distance. CLIP does 0.6, and Uniter from a couple years ago does 0.7. So pretty good. So this is kind of interesting. Again, this is all zero shot, all using some variations of a text image matching objective. But one thing I want to say is that even when our model is wrong, according to what the crowd worker said, it's kind of interesting, and we can use it to kind of gauge what it might be thinking about, I guess, in terms of events and situations. So here's an example. I went to the fair with my kids last weekend. There were a lot of people there. They also had a barn. We got to see a lot of animals. We can't wait to go back later. And so this is the order that our model puts it in. So you can see that the first 3 images that I put it in are the merry-go-rounds. Now it doesn't match the barn image with the barn. It matches it with 4. We got to see a lot of animals, and that's kind of interesting. And I think the reason is it's because it's thinking that people stay on the merry-go-round for a while. People don't like suddenly get off the merry-go-round, go to the barn, and then go back on the merry-go-round. And so I kind of think this makes sense. It wasn't what the crowd worker said, but I would kind of disagree a little. So it's kind of interesting. Cool. And so going a little bit faster here, we tried our model on a lot of fine-tuned video QA datasets, and we get state of the art on pretty much all of them. In some ways by a couple of percent. So it's kind of interesting. And I combined a couple of things from the paper because yeah, we did a lot of experiments here. Last but not least, we tested our model out on visual common sense reasoning. So this, to some degree, is an interesting task for our model because our model is never pre-trained on images or never sees any captions. So it has to do this through fine tuning, but still it does quite well, 65% on Q to AR, and I'm just using the same size models for all of these without any ensembling, and it beats all the others. So despite no supervised object detector, and despite never seeing still images before, our model does pretty well. So last but not least, before we get into some discussion, we have a little bit of ablations here for kind of what works and what doesn't. So that contrastive vision and language loss, the first objective where we're learning kind of the lower level recognition level stuff, is really important. On the TVQA plus data set, it gives you 8% improvement if you have it versus if you don't. On TVQA, if you only train it and evaluate it on one video segment, our model does 1% better. And I'm not sure quite whether this says anything about like TVQA or just our learning paradigm, but what I think is that letting it contextualize from multiple segments at a time means you get better downstream performance. You just have to be careful about the way you mask. That's something we talked about in the paper. Now, this is, I think, is maybe the most important message here. We tried our model, but trained on how to 100 million, which is a different data set of about 6 times smaller. So the name is 100 million is a bit confusing. There's actually only 1 million videos, but it's all within the how-to domain. And we kind of covered a more diverse set of videos. This more diverse set of videos plus using more data gets you 4% improvement. If you were to train our model exclusively on captions, using the biggest data set I could find or use, which was conceptual captions, we only got 44%. So. Last but not least, and perhaps this isn't super surprising, the performance increases a lot with the number of epochs. And so I guess that if I were to train it for even longer, performance might still go up. Yeah, so that was the MERLOT section of this talk, and I'm just going to have like a brief little bit of like discussion synthesizing these, and we can kind of chat more. There's pros and cons to learning both from simulation as well as from videos. Simulation's nice because you get to learn to act and not just see and write. And you could imagine models being more interactive here than what we did. Models could guide the training loop, maybe using like curiosity or kind of some kind of active learning approach to guide which things are explored and which phenomena the model tries to study more. Cons: you have limited vocabulary in simulation. So there's only so many objects in THOR, there's so many actions, etc. Whereas on videos, there's so many objects and actions that people do in the world. And it can be hard to learn human behavior here. So we can learn all we want that cups have liquid and they can be emptied, but we can't necessarily learn, or it's more difficult to learn what people do with cups. People drink from them, etc., and what kind of norms and stuff are involved. Now, web videos, I would say, are kind of the opposite here. You have a super wide vocabulary, and you can learn not just object level knowledge, but you can learn human norms, behavior, and events. And those cons are that you can't participate in the video. You can only write and see. You can't act. And so you're kind of, it's kind of, I guess, the complete opposite of what we get from simulation. So in a sense, I think that there's some pretty exciting future prospect of combining the best of both worlds with kind of a joint simulation web video training approach. I think that sounds really interesting. Now, one more thing that's super important here, I think, is privacy. And within this category are also other negative societal implications of training on multimodal web data, which we thought about a lot for this work, and I think I should briefly discuss today. We did a couple things to to put a Band-Aid on this for MERLOT, to allow us to kind of study the implications of this kind of web scale or video scale pre-training without having hopefully too many privacy issues. So first off, we curated data focused mainly on big channels that were more like for commercial use with celebrities, et cetera, people making money off of it, not random people. And so this is kind of a deliberate decision that, and we kind of analyzed how well this worked in the appendix of the paper. It worked pretty well. Most of the channels that we used had quite a lot of subscribers. And we focused on a public platform that people expect is public. So not only do the terms of service, say people can download videos, but also people who are people have kind of studied how the YouTube community views privacy, and people generally expect that their videos can be downloaded by whoever. So it's maybe a little bit more open than say like Facebook or something. We also did this at a scale so that people are, to use the terms of Marwick and Boyd, in public without being public. So kind of like the difference between being, I guess, like stalked versus being in a crowd. The idea that we had here is that, okay, maybe it's a little bit better if we just use a lot of videos from different people rather than training our model exclusively on videos from one specific person, because hopefully kind of all of the person level stuff is kind of washed out by the scale. Now, the next thing we did was we distribute links, not to the videos, to people, or that's kind of our plan, to allow users to have the right to be forgotten. So if someone doesn't want their video to be, I guess, downloaded anymore by anyone, they can delete their video off YouTube, and then it has to be removed from our data set as well. And so we did this, again, because we're trying to allow for some safe research now so we can encourage future work into what these kinds of foundation models can do, what the benefits of them are, and what the dual use risks are. And again, not advocating for product use right now. So there were some issues with the things that we did to allow for better privacy. Focusing on big channels meant we got a lot of local news in our data set. And local news has some bias issues, kind of what content is picked up by local news stations in the US and what kinds of content aren't. Moreover, there's inherent bias on YouTube. If you're just training on web data in general, it kind of, the traditional way of doing it kind of encodes this way from nowhere that's been, view from nowhere that's been discussed pretty recently, echoing back to some ideas by Donna Haraway in 1988. And this bias is amplified by the culture we live in, but also by the YouTube algorithm, which kind of plays a big role in controlling what kind of content goes viral, and then therefore what kind of content exists on the platform in the first place. So it's kind of like bias comes at a variety of different levels of our filtering strategy, and we're still trying to like dig more in terms of how that bias is expressed by our model. Again, this is why we're not advocating for product use right now. So I think there's a lot of important future work here, studying privacy, bias, and dual use. And you could imagine maybe possibly a mix of technical and non-technical fixes. So like maybe differential privacy is interesting to explore. But also maybe it's the case of we just need like better regulation and better knowledge by both policymakers and the general public about kind of what these models can and can't do, what the risks are, and yeah, what it means to upload data to the internet in the first place. And hopefully, again, this is the beginning and not the end of this key conversation. So I think it's probably good for me to leave it there and ask for any questions. But first, I want to thank everyone I work with, and thanks to you all for having me here.
So thank you. So any questions from you? Hamid?
Yeah, I have a practical question. While you were downloading 6 million YouTube videos, did you encounter any problems in terms of how many times you can call the API to download those videos, or like how long do you take?
Yeah, a lot of problems. A lot of problems. There's yeah, like We did this kind of scraping over a long period of time. I think we kind of more or less started this project in late 2019. And yeah, it took 2 years.
Yeah, so the reason that I ask, if you guys just release the URLs, then what do you do for the other researchers to not go through the same 2 years to get access to the whole data set?
That's a good question. And I've since found better ways for things to be faster, and I'd be happy to share those with people offline. I mean, I think just like the other thing, I mean, the thing about, right, like is yeah, like I think I would like there to be kind of some way for like for there to be like some set of norms that we as a community can agree on to be able to fairly like release this data set while also protecting like user privacy. And I feel like this is like one set of norms, and I imagine that like you know, maybe there'll be more papers that come out that have different sets of norms, like similar to how in the text domain there weren't really that many like giant text data sets until maybe pretty recently, actually. I don't know. Yeah, there's definitely a lot of trade-offs between, say, reproducibility and what is it? And privacy. But one thing we do have is we have our we're happy to share kind of our algorithm for how we filter YouTube videos. So that could allow potentially for people to make data sets that are identical in ideal distribution, I guess, to what we used, even if it's not, you know, exactly the same set of videos, even if they say only overlap like 98%.
Great, thanks.
Yeah.
Hi, Rowan. May I ask you a question? So,
yeah.
So from the two works you just described,
yeah,
and I feel essentially they share the similar structures. Basically, you're trying to turn the image into the words in different ways, and then trying to solve the problem by leverage the words relationship. You know, so. And many language VL programs related to this is they first turn the image into a bag of words implicitly or explicitly. So I want to ask, have you guys find any principles behind this? Like for different tasks, the image will turn to text in different ways. So let's say for this type of task, and the image will have to convert to the bag of words in this way. Otherwise, you know, for the other couple tasks, you need to turn the image into bag words in a different way.
Sure.
So exist such kind of principles?
Yeah, like, do you mean like, maybe the question is like, to what extent we can get away with having a universal image encoder for any task?
I guess, so first of all, if such a universal image encoder exists or not. If not exist, that means different tasks requires different encoders. And is there any principles to guide you to figure out, oh, they usually use this image encoder for this type of VL task, and for others, you know, etc.
Yeah, it's a good question. I feel like I'm inclined to believe that there ought to be different image encoders for different tasks. But on the other hand, it might be some fiction that we can get away with. Like if we just had a big enough model, maybe you could say said image encode, like said, I guess, super image encoder contains all the sub image encoders that you would need for everything from VQA to, I don't know, captioning to VCR, etc. So I don't know. I think that probably right now we're probably at the point where you could just make the image encoder really big, and that would probably solve the problem in the short term. But I think there's something unique about us as humans, as like we can kind of look at an object in a completely different way if we're given a question about that object or given a description about that object. Like we were really good at thinking outside the box in that way, given a specific prompt. And that's something that I don't think is captured by this kind of, I guess, super image encoder idea. So I don't know. Yes and no, yes.
But you mentioned that the big, very large image encoder. So in terms of the very large image encoder, does it mean it assign more words to each pixel or each patch of the image?
Yeah, I mean, I guess, right? Well, yeah, I mean, I guess you could think about it like that. Sure.
Okay, thank you.
Hi, Rowan. I guess I have another question regarding to the so regarding to your data. So how did you feel the quality of your pre-training data? And so when you pre-train the video so when you pre-train your model, did you guys try just training everything from scratch and then try to learn a video encoder instead, so that it can be used for video understanding task?
Oh, what do you mean? Sorry. I think we did pre-train, like we did pre-train everything end to end, but on like all of these objectives are learned at the same time, but like with a sparse sampling, I guess, or frame level approach for sub-selecting the image frames. Does that answer your question?
Oh, I see. So
Yeah.
you mean your video encoder is totally pre-trained from scratch? So there's no pre-trained initialization.
No pre-trained initialization. I think we did experiment with initializing the language side with Roberta, and honestly, I'm not really convinced that really helped at all. Image encoder is completely from scratch.
Then did you try so test your model on some video understanding task?
Oh, like without text.
Mm-hmm.
Yeah, actually, I think we might have. I think Jack might have been doing some, like one of my co-authors might have been exploring that. And I'm not quite sure how well it does. I have to ask him. I definitely think, yeah, you might be able to, depending on the task, it might be able to do pretty well. But I know that there's a lot of video only tasks you can often get away with just a couple of images, and they're or like say like if it's I don't know, people playing basketball, you can get away with recognizing a basketball hoop. And so I'm not quite sure that our model would outperform the baselines there, but I don't know. That's cool to explore.
Yeah, thank you. So any more questions from the audience? Okay, then I think we are pretty much on time. And then so let's thank our speaker again. Yeah. So and I think we also have some one-on-one discussion later on. So tomorrow. Yeah. So thank you for your virtual visit. Yeah. Bye bye.
Thanks. See you, everyone.
Yeah. Bye bye.
Thank you, everyone.
Thank you very much.
Thank you.
Thank you. Bye bye.